Welcome to the CNPS 2019 conference in Seattle, Washington, here at the University of Washington. My name is Bob Hilster, and I am your resident mad scientist, here to make a presentation on a circuit using the particle model to explain circuit theory, and then a supporting experiment. In general, I'm going to briefly describe this circuit using a standard explanation, then a particle model explanation, which is mechanical, and then an experiment using three resistors, large, small, medium resistor, and then give you the results. This is the circuit I'll be talking about for the rest of the afternoon: a 9-volt battery driving a 2K, 3K, and 4K resistor. With 9 volts and a total of 9K, you get 1 milliamp of current, which is shown here on the equation down here. I haven't got the pointer yet, which is shown down here. And the current is just, again, the voltage divided by the total resistance, and the sum of the voltages, the battery voltage minus the voltage drop, must be 0. That's true in the particle model as well as in the standard explanation. Okay, the speed of a signal in the circuit gets very confusing. From this link, I see that it states everyday electronic devices, signals or energy travels as electromagnetic waves, signals or energy. And they travel at the speed of 50% to 99% of the speed of light. That's what they say. The electrons themselves drift much more slowly. In fact, the same link explains drift velocity. It's the average velocity attained by charged particles such as electrons in the material due to the electric field, presumably the EMF force. That drift velocity is only 3.2 meters per second. That's very slow, and I visualize the electron hopping from hole to hole at 3.2 and change that around to a signal that's happening the other way at 50% or 99% of the speed of light. And I'm sorry, that doesn't make sense. My assumption in the particle model is that the speed of the electron, or in my case, the particle, G1 particle, is probably always moving at speed c, and is only going slower because its path is not straight. Okay, the TPM, the particle model, and the G1 particle. It functions in many different ways in the particle model. It is the gravity particle, which comes at us as a low-intensity rain of G1 particles. It's used in a particle in light as a stream of G1 particles with a repetitive pattern. It's used in a magnetic field as individual streams of high-intensity G1 streams spinning around and through the magnet. And finally, as in this talk, it's used in the circuit like a fire hose, a blast of G1 particles just plowing its way through the circuit, all moving at speed c. The overall speed of the wave is probably slower only because of its path, because it probably never goes in a precisely straight path. The electron, oh, that's backwards, sorry. Excuse me. Okay, the particle interactions. These are the same interactions I'm going to be using throughout, I use for gravity, light, magnetic fields, and circuits. As a G1 enters an object, like an atom, a molecule, or larger, they can pass straight through. They can hit and scatter, or they can get trapped as an orbital, and it all depends on where they are, what direction they're going, and what distance they have from the atoms inside the wires or the component. Okay, this is an example of the G1 particle passing through the resistor. It comes in this way, passes straight on through. Most of them, in all cases, not just every component, inductor, capacitor, most of them pass through. Some of them will come and hit and scatter. Some of them, if they're the right distance, the right direction, and the right velocity, they can actually get trapped. This is something that's needed for electrostatics. In electrostatics, if you get a lot of electrons being accumulated in a balloon, they're supposed to be there, and they show negative signs all over the place, just sitting there like they're waiting for a bus to come along and pick them up. My contention is these things are moving fast, and the only way they're going to hang around is if they hang around as an orbital. Those interactions are the same interactions for gravity, magnetics, electrostatics, and circuits. Okay, G1's lost through a resistor. We're back to the circuit. Now I'm going to explain it in particle model terms. We have G1s being shown here going into the 4K resistor. And as they pass through, they're going to do these same things. Either pass through, most of them pass through, some of them are going to hit and scatter. So most of these pass through this resistor, some hit and are scattered and are lost. It starts in here with a quantity of B. It loses some, it now has C. Same thing happens here. The C enters, you lose some, you get D. D enters, you lose some, you get E. And then in the terms of my spreadsheet, I make E equal to A, and I continue this another cycle. Most of the G1s pass through, a few hit and scatter. What really surprised me when I applied this was the fact that when they hit and are lost, that the loss of G1s is just like the loss of voltage. You have a one-to-one correlation, in a sense. You lose one G1, you lose some part of the voltage. That surprised me. I did not expect that to make such a direct correlation. But based on that, I decided you could equate G1 loss to volts and assign a value of volts for one G1. Just as a caution, there is no physical property of the G1 that demands a voltage assignment. There's nothing there. There's nothing physical. And I really don't know what the value should be. I'm actually going to try to find it in a second experiment, which didn't work out, and I'm going to have to repeat it, but I don't know what the value should be. I just picked a value on my own. It's a nice, neat little number of 0.1 volts per G1. So if you're going to lose 1 volt, it's going to be because you lost, hit, and scattered 10 G1s. And for this circuit, when the number B enters the 4K resistor, it's supposed to have a 4 volt drop, and therefore it should lose 40 G1 particles on the basis of 0.1 volts per particle. And here's the second surprise. If you're going to lose particles here, 40 through the 4K, 30 through the 3K, 20 through the 2K, you've lost 90 particles in that circuit. That doesn't sound like Kirchhoff's law, where things are supposed to add up. And it dawned on me what the battery must be doing. If you're ever going to reach stability in this loop, you have to gain 90 in the battery. I was never taught in electronics that a battery adds electrons as it emits them. I was never taught that. But if it does add, then if A comes into the battery, then 90 are going to, the number 90 because of 0.1 volt per G1. And so A plus 90 is B, and C is B minus the loss, and D is and so on. That formulates the equations for the circuit in the particle model. Two surprising effects. In summary, losing G1s is a loss, gaining G1s is like having a battery or a power supply. And so these are the equations I can develop for the circuit. The G1s lost, particularly going into the 4K, where B is the number entering, I is making the statement that is proportional to the ones entering times the resistance. And the total number lost, though, this is a proportionality. If you want to make an equation, you have to have a constant of proportionality, and that constant I named the interaction factor. By the way, I have an interaction factor for my gravity equation. And if you can make this as the number lost is equal to the interaction factor times the number entering the resistor times the value. The voltage drop then is simply you multiply the equation both sides by VG1, you get the volts across the resistor is the number entering, the interaction factor times the resistance times VG1. And it's simply, to get the current, you divide both sides by R, and current is B times IF times VG1. The items in red are two numbers I don't know. Two numbers that we need to find out. I need to find out, and I would hope to get numbers for them. For the time being, I make an assumption of what they are so I can do an evaluation and see how this works. So these are the circuit equations that I implement in a spreadsheet. And I'm just repeating essentially, although it's looks more complicated, but it's simply algebra. This is only algebra. The output of the battery B is equal to the input times the voltage of the battery divided by the volts per G1. The output of the 4K resistor is equal to its input minus its loss. That's the same loss I showed on the previous slide, and you simplify it to that. For D, it becomes the same for the 3K and then for the 2K, and then I make the next A equal to the value E as it goes around the circuit. And what you really see here is an effect in the circuit where the final value E is a product of three different losses through the resistors. This is a way of showing that there is shielding going on in the circuit, just like there's shielding in gravity. So now, what's the value of A? A is the number going into the battery. What's the value? The battery doesn't know the value of the components. It doesn't know it. It doesn't know what's out there. It could be one resistor, it could be nothing. It doesn't know. The components don't know what the battery is. But somehow the circuit works. So the question is, how does the circuit know how many G1s it should provide in the whole path? I highlighted the word circuit because it's the circuit that knows, not the battery, not the resistors. It's the circuit that does. So here's what I have. I'm going to present. I'm going to take a little bit of time, and I hope later on today or tomorrow you each can get a chance to play with this, because it's very interesting to see. I have a spreadsheet I'm going to show, and this is the title to make sure I get the right one. And I am assuming these two values, 0.1 for volts per G1 and an interaction factor of 1 times 10 to the minus fifth. And the interaction factor has the units of 1/ohms to make the equation work. So I am going to change this. Patience. And here's the spreadsheet I used to actually do the calculation for the circuit. I have it blown up so you can't see the whole thing, because if you saw it, you couldn't read it. Here's A. Is that going to click on it? Oh yeah, it is. Here's A, and I automatically just said 2,000 G1s are going to be entering the battery. Here's the volts per G1. Here's the battery voltage of 9. You can simply do that calculation, and you can see there I take C4 divided by B4, and you get 90. So B is the output of the battery, and it's the sum of A, 2,000, plus the 90. You have 2,090 going into the 4K resistor. Into the 4K resistor with an interaction factor of this, and that's the resistance. I can calculate how many G1 particles are lost when 2,090 have entered, and that's 83. And so I could go through the 3K, and then I can go through the 2K all the way to the end if I can get it over there. And I get my final value of E. I started at 2,000, I'm down to 1907. Now this is a smart circuit. That's because I'm inside the circuit telling the circuit what to do. And I actually pre-calculated here a value that would help accelerate the process of getting to a stable point. Okay, so I apply that K value over here to the 2,000, and I get 985. And I go down, and every cycle, and that's all the cycles I ran was, looks like 8 cycles. And I got the answer, only because I pre-calculated. It says that if the battery receives 939.46, etc., it will give you a, guess what? It doesn't give you a 4-volt drop. The standard model says that's a 4-volt drop. The particle model says no, there's 41 particles lost in the first one, not 40. Why is that? Because there's more lost on around. It can only lose 90 going around. It's going to lose 41 here. Oh, come on. Help me. It's going to lose 29 here. It's supposed to lose 40 here. It's supposed to lose 30. It loses 29.6. And here it's supposed to lose 20, and it loses 19.1. So what you see here is you have more loss on the first resistor, then less loss, and less loss, and you have almost 1,000 G1 particles flowing around and through the circuit. You need that 1,000 as a base. Otherwise, you wouldn't even get close to the right voltage values to match the standard model. Okay, this second one here, if I get over there, this is the dumb circuit. This is the way it really would act. And I've only done, I don't think I've done maybe 8 steps here. But I started very close to 939. And you can see that 940 works down to the 937. I don't quite get, this was the 612, 45612 here at 74273. But it's getting close, and I don't know, I mean, I'd have to go on down further to show you how many true cycles it would take. Okay, let's try something else here. Back up here. Let's say that the circuit for some reason starts with 500 500 entering the battery. If there's only 500 in the battery, it actually works its way up to 939. The circuit will find the value of 939, whether it's low at 500, starts at high at 1000. The circuit will stabilize at 939 each time. To me, that is actually just quite remarkable that it could do that. All right. Here's what I do. Yes. Okay. By the way, again, I offer anyone who wants to sit down and play around with those spreadsheets and see how it works, you're welcome to do that. So I'm going to do an experiment because the particle model predicts a higher voltage on the first one, then a lower one and a lower one. I'm going to do an experiment. The first step is to place 3 resistors in this order. First a large, medium, and small. I'm going to measure the resistance of all 3 resistors. Then I'm going to connect the battery. Then I'm going to measure the voltage and measure the voltage drop of each resistor and record that. The second step, which is, get my pointer back. The second step, I'm going to reverse the large and the small resistor, leaving the one in the middle alone. Then I'm going to repeat the measurements. And this is what I would expect to have happened. I made the numbers simple where I started with 1000 as an input. And you get 1090 into the 4K. If the 4K is there, you're going to lose 40 and you're going to be at 1050. And there's the 3K, you're going to lose 30, you're going to be at 1020. I'm reading the black numbers. And then you're going to lose 20 and you're going to be back to 1000 and the circuit is stable. Then I'm going to switch the resistors. I'm going to put the 2K down here and the 4K up here, and I'm going to start with the same 1090, which, by the way, isn't correct, but that was my assumption at the beginning. Start with 1090, and instead of losing 40, I'm going to lose 20. So I end up with 1070, then I'm going to lose 30, and I got 1040, and then I'm going to lose 40, and I'm back to 1000. It's stable as well. Standard model is going to tell me that, no, this is 4 volts when it's here, and it's 4 volts up here. This model says no, because I got 1090 coming into the 4K here, but I only have 1020 coming, 1040. It's 50 different, fewer particles coming into the 4K when it's in position 3. Well, what I did was I used 15 sets of resistors. Took 15 sets, and I rented a 6.5 digit voltmeter. And that's a picture of the voltmeter, and that's my test setup. And I should have got a 7.5, but that one cost me $150 a month to rent. The 7.5 will cost $300, double that. This is the circuit I used, the circuit board I used. And this is a closer look up. It's the same one. It's for actually the different experiment, but I have a battery over here. I connect the battery through a resistor, and I tag the resistor with a nominal value so I knew what I had. This had a strap in it at the time. The other resistor was laying over there, and then the third resistor back to the battery. That was a test setup. I did 15 different circuits, and there's the 15 results. And there's circuit 1 all the way down to circuit 15. I measured the voltage this is for the large resistor, the 4K. They're not all 4Ks. There are a whole different series of voltage ranges, high current, low current ranges, and you can tell that just by the value of the voltages listed. the measured value of the large resistor when it's in position 1, and when it's in position 3, I measured its voltage. And I would predict that if you subtract the voltage in the third position from the one in the first, it would always be positive. And it didn't always turn out that way, but it didn't turn out bad either. This one turned out negative instead of positive. So did this one and these two. There was 2 of them that were exactly equal, no matter which position they were in. So it didn't come out quite like I liked. But then I went to that same spreadsheet I showed you for each of those sets. Plugged in the voltages, the resistor values that I measured, the voltage values and resistor values, and I had the circuit equations calculate the voltage drop. And so I get, this is the value of voltage by that circuit, by the TPM equations. And ironically, this one, it did come out positive. Here it's positive, here it's negative. That's clearly an error, okay? All the ones that are black are positive. I expect it to be positive. This one is negative, but here's really interesting. C7, the particle model says with those particular resistors, the particle model predicts it's negative, and the measurements I made by the voltmeter in the circuit were negative. So even though they're highlighted in red, that's not an error. That is correct. In fact, these 2 are correct. In principle, I could have said there was only one real error if you ignore the ones that were equal and get a very high percentage, but I said, okay, I'll just say there's 4. There's 4 here, 4 in red here, 4 in red here. Take a conservative, conservative statement, and it's only 73% correlation. I say only. That's, if it were 40, 50, 60% correlation, you could argue that's maybe in the noise. You're down at a low level of the meter. You don't know what kind of values you're going to get. But 70%, 73, and even I could claim that 14 out of 50 were actually correct, and get a very high percentage on the large resistor. Small resistor really surprised me. Did the same thing with the small resistor, measured it when it was in the first position and in the third, and I expected it to be positive because it has fewer, on the model I showed you, it has fewer particles coming in. I got negative all over the place. I said, wow, that really went bad. But then I did the particle model equations. They also came out negative. Okay, so all the ones that I thought were bad over here that were negative aren't bad if they're shown up negative by the prediction. There was only 2 positive here, and the C1 fails again. But if you look at it, although this is marginal, both of these are very small numbers. That's only got an 8 digit there. This has a digit 1, and these have bigger digits. But okay, so there's maybe 2 errors, 86% correlation. The particle model predicted the voltage measurements to a 70 and 80% correlation. Well, so my intuition about that small resistor was wrong. And the reason was that you don't get the same number. I said I had the same number coming into B, 1090 for both. It doesn't come out that way. The reason being is that the percentages in that equation, you had 3 equations, 3 terms, they multiply different. And when they multiply different, it won't stabilize until all the drops are 90 to match the battery being 90. And I didn't take that into account when I first looked into the experiment. Conclusion, big conclusion. This does not prove the particle model is the correct model. Doesn't prove it. What is needed to prove something is direct evidence that there is a particle, like the G1, and it interacts with the circuit as I described. What is needed is direct evidence of that. What I have is the paper describes only indirect evidence. I don't have direct evidence. But it's quite amazing to me to be able to use a 9-volt battery, 3 resistors, to provide evidence that supports, I claim it supports, the particle model's explanation of the circuit. Thank you for your attention. Any questions? Musa?
Yes, very interesting. It gives one an insight as to what might be happening in a circuit. My problem here is, how do you explain the magnetic field around a current carrying wire?
Well, I do have a video on that. If I go under the name Particle Guru, one of the first videos David had me do was to explain the magnetic field through a wire. Now, it'll take a few minutes if you want me to go through it. First of all, you have a copper wire. And the copper wire that we make is very well organized. It's got atoms that are placed nice and neat. Resistors don't. The resistors are all messed up, but a copper wire has atoms nice and neat.
Closer.
Thank you. Very, very neatly organized. Now, it's the particle model's contention that the G2 force field surrounding the wire is the thing holding those atoms together. It's a gravitational field inside the wire. Now, my talk here didn't talk about that. My other videos as a particle guru do talk about it. But because there's this G2 gravitational field inside the wire, that G1 particle is guided by G2. G2 gravity can bend G1s, it can slow them down, and it can speed them up. So as it goes through this copper wire, which is very well organized, the path it can take is more of a spiral than it is a straight line. Just like an asteroid going through our galaxy will find its way through. That's one of the reasons why I say a particle can be moving at speed c and still measure less than c as a wave. So what happens in the wire is you got them spiraling one way. If you take the G1 particle, it spirals the other way, and you'll find that the spiraling effect matches the magnetic field. Where does the magnetic field come? Remember, particles can pass through anything. G1 particle can pass right through the Earth, pass through a resistor, it can exit the wire, and it has a specific trajectory. When it exits, the G2 gravity surrounding it holds it as a magnetic field, which in my opinion spirals out. And as long as the battery keeps supplying, you'll have that magnetic field. That's my explanation that I gave in the video. Look up Particle Guru and look up, the title is The Left-Hand Rule Becomes the Right-Hand Rule. I believe that's what it is.
I'm not going to remember that. Just look up.
That's my answer. You will get G2 fields around a resistor, but the particles, when they get through, they're not spiraling, and they don't have a trajectory that's going to come out this way here, come out this way here, come out that way there. So where does a magnetic field come from in the particle model? comes from the battery feeding the wire, escaping, and being trapped by the gravity field around.
Well, it sounds convincing. But, it's a good attempt to convince how the magnetic field comes about.
Well, there's a lot behind that. You know, I worked for 10 years on gravity before I even worked on light. But once I started working on light, I was able to apply the gravitational interactions to refraction, to prisms, to magnetic field, to electrostatics, to circuits. And I've even explained partially battery and electrolysis using this particle model. Once you get the feeling all the way across the board, and it seems to work here, here, and here, it gets pretty compelling. But you can't prove it. I have no direct evidence. For this experiment, for the magnetics, I have no direct evidence. I can't see that particle going through and doing that. Don't have it. A lot of people will have less evidence than that and claim they have the whole answer for the world. But they don't have direct evidence, they don't have absolute proof. They just have a theory, just like a model, just a model.
I think one of the things I know, because I work on the model with my father, is that there's a great confusion that when you talk about gravity, people do not get it, there's a different level. When you go down to the subatomic level and you're talking about what we call electrons and protons or nuclei, that we have another level down of a different particle, smaller, faster, that creates gravity. So if you were to make the sun a nucleus and planets electrons, that there is another particle, much smaller, maybe going at c squared, that controls those particles at that level. So that's why we have G1, G2. Now this is extremely similar to Borkert. It's not a coincidence. That was one of the things that we subscribe to, is infinity. Borkert describes ether as A1 at this level. That's what we would say light is. Then what makes ether and those things bend A1, he has another level down A2. If you read his book, you'll find that out. So when we talk about a gravitational field G1, I think people sometimes are thinking, oh, you've got gravity, that's like saying gravity works at all levels. No, gravity, the concept of gravity being random particles in random directions causing gravitational fields happens at all the levels of the universe. It doesn't mean every level's the same, but it means that the reason light bends in a prism is not because the G1 particles decide they're going to move. They are like, you imagine a giant a prism made out of suns, all put together in a lattice-type structure, or held together by the particles going around them. And when you get a G1 particle, or waves of particles coming into that prism, there is a force field. It's just like setting up a bunch of suns, and you send asteroids toward them, or whatever you want to call comets, and when they get closer, they bend in, and that bending we have a description. But the gravity we talk about as G1 is a different particle at a different level. So it's very important, I think, for people when we're talking to understand that. I think what happens, they'll hear gravity and they go, oh, well, they use gravity for everything and it's the same. No, it's not. I think that's sometimes confusing to people.
Okay, but I want to make two more comments about some videos I have. One of the videos I have is about Coulomb's law. Every one of you who have been in electrical engineering class, when you see Coulomb's law, force times is equal to a K constant times charge 1, charge 2 over R squared, everybody says, oh, that's just like gravity. When you look at G2 gravity, which is a lower level down, it is that equation. That Coulomb's law is equivalent of Newton's equation at level 1. Level 1 is Newton's equation, Coulomb's law is the equation, because in all the applications I've seen, the electric force between plus and minus, as described, often occurs at the same place where I show G2 gravity pushing the G1. Not always, but it often appears at the same place. So it's what the standard model today has, and they have an equation for a lower level, and it looks like gravity, and they say, oh no, it can't be gravity, and they go off with charges and the rest. But in fact, it would be an equivalent equation for level 2 gravity. But in our case, it's caused by a different particle, G2 particle, which, by the way, is in my opinion, it's just an idea, that it comes from lower level atoms. Here's our atom this big, and here's a lower level atoms. It has an orbital that has to move very fast. And when that atom splits in a sun, those lower level orbitals are the G2s that are emitted from the distant stars. Now I'm sitting here. I think we're done, Dave.
Any other questions? Okay, well, thank you very much.